with Intimo, which is a company that sells a surgical simulator. So the team DEFROST is located in Lille, in the north of France, and we are doing modeling, simulation, and control of deformable robots. We have background on robotics, numerical mechanics, computer graphics, and control theory. And breaking news, we are organizing a summer school, if you are interested, on July 4th to 8th, which is called Deformation in Robotics. And the title has not been chosen it has been chosen because it means something. It's more about how we handle deformation in robotics in general, including in rigid robotics, because in rigid robotics some people are looking at kind of manipulating deformable objects, also, or for instance in surgery, how you take into account the deformation of organs, etc. And I think we could do a link between these people and our community of soft robotics. So in the team, we are trying to do some robots. Oh, I don't know why the video are not functioning. Okay. For some reason, the video are not starting on the other slide. I don't know why. Okay, sorry for that. So we have a set of robots. I will just describe this. In particular, so trunk, anisotropic robot. We are also trying to do soft robots that mimic the behavior of organs. Like here, it's a prostate soft robot. So during the insertion of needles, it inflates, and we are trying to use that. It's a compliant spine robot with cable actuation. We are also looking at parallel structure. So parallel, here a haptic device with a direct actuation, and here it's for instance a finger that you can put on a gripper. So all these robots, I would like to insist on that, are more or less prototypes that we are doing in the team, but to validate often our software, because again, the team is more focused on the software part. And in the contribution we made in the team, there is recently we've been working on trying to make a model, like FEM model, compatible with real-time computation that is needed in robotics. And there are some numerical techniques like model order reduction that allows to compute such complex story. The quality of the display is not there. But you can start from a very complex model. It's complex in FEM for some reasons that are more numerical. And in a robotics point of view, you can say, okay, maybe among all these thousands of degrees of freedom of my FEM model, I just care about 30, 40 main deformation modes, and that's my new degrees of freedom. We've been working a lot on inverse modeling, so trying to find how to move the robot, how to actuate the robot so that it follows a trajectory, it follows a position. We have extended that with a contact, so you can follow a trajectory and put contact. We've been working also on Coursera model, coupling Coursera and FEM. Now the video are. I think my computer doesn't like things. Okay. Anyway, so you don't see all the videos. Just I wanted to mention that here it's a video that shows the force measurement. So we make the soft robot can be a force sensor because it deforms under the pressure of a force. So you can observe the effect of a force, and through an inverse model you can guess what is the intensity of this force. And we also work on a closed loop model So like here to follow a trajectory, of course, you can follow what the model is giving, but if you are using closed loop approach, you can be much more precise. Okay. In fact, in what we are doing, our motivation is to have a modeling and simulation in the life cycle of a robot. So first, during the design phase, you can use simulation for doing the sizing and evaluate the performance of your design. Then when you are happy with this, you can use inverse modeling to evaluate the workspace, to validate the model of the design of your robot. Then you can go back to your CAD if you are not happy. And you can also directly on the virtual robot implement control laws. And it's more like a real-time clone. And then you can really test your control law directly on the robot without having it fabricated. And in people that are working in computational embedded intelligence, for instance, or morphological computing, you do want to have this kind of framework where you are able to emulate the law, the control law inside your environment. And now that you have fabricated your robot, you can use it, and your control law, I don't know what's happening. I suppose here is the control law, you can use it in your real robot. The inverse modeling, it can be used for the definition of trajectory with or without contact, for doing the estimation of posture with force sensor. And the simulation, you can use it to basically implement your robot in its environment of use. And it's highly used in ridge robotics, this function, and methodology to simulate the robot in its environment. So insofar we are using a methodology which is based on Lagrangian mechanics. We are using constraint-based deformable model, but I say deformable model, but it's also true for rigid models. You can use except for rigid model. It's based on the second Newton's law. Basically, if you have a FEM model, you fill this value with your force of your FEM model, and your actuations, the actuation of your robot, are defined by Lagrange multipliers, which is an interesting framework because using Lagrange multiplier, you can say that the actuation is one of the unknown of your system. And that's why we choose this framework. And basically, as soon as you use that, you can use an optimization that will find your lambda value. And in fact, insofar we are using a lot of projection. It's something that is also available in Lagrangian mechanics, but we are using a lot of that. But if you look at the equation you obtain after the linearization of the problem, so basically at each time step, we'll linearize the system, but we will again update this linearization at each step. It's what is shown here. It's not really important. What is important is at the end you obtain a big matrix system, A bx equal B, plus your Lagrange multiplier, each time A x equal B. So here it's in quasi-static and here it's in dynamic. But that's not really what is important here. What is important is that you have two types of projection. One is stiffness or mass projection. Here you project here the system of equation in a reduced state. It's what we do when we do model order reduction. You take a big system and you project it in a small space. And it allows to reduce a lot the degrees of freedom of your system. And there is another strategy which is called compliance projection. And here you are not, you are selecting subdocs that are interesting. For instance, if you are using cable on your robot, you want to know the compliance of the structure, but just from the point of view of your cable. So if I impose a force on my cable, I want to know what displacement I will get on this cable. And for that, in fact, it's like you have to compute the whole structure, but from just the point of view of your cable. And it's what is done in compliance projection. Here in fact, we project the inverse of this matrix. Here we project the matrix. And when we do compliance projection, we do use the inverse. And with these two stiffness projection and compliance projection, we are able to do two different things. One is to reduce the size of the problem and make it fast to compute. Here, the idea is to be able to write all the optimization in the reduced state of but without considering all the other degrees of freedom of the result. Okay. Now I will do a live demo because it's more funny. Okay. Can you? Okay. So this morning we had a workshop, and for those who were not able to come, I wanted to show you very rapidly what we can do. In fact, if you want, we can. So we can give you access to a binary where you will be able to start like this, and you have different type of scenes here. And what we have this example of a soft robot. So it's a kind of hybrid robot. And just to show you the pipeline of what we obtain at the end, we have a maze